decide to meet the deadline as well as to handle these panel bursts. Let us discuss how some of the current approaches handle OLDI. Below TCP is deadline agnostic and has a long latency here. TCP timeouts are too slow to detect conditions, and on detecting conditions, TCP closely overreacts to it. It cuts the window in half. Datacenter TCP, D2TCP, particular SIGCOMM 2010, is the first paper to comprehensively address the problem of fair latency. The idea is to finally vary the sending rate based on the extent of conditions as opposed to TCP which closely varies the sending rate based on the mere presence or absence of conditions. It's a cool idea and it shortens the tail latency by a great amount, but it's still not deadline aware. Therefore, a significant fraction of flows still miss their deadline. In fact, from our experiments, we find that as much as 25% of flows miss their deadline when the deadlines are tighter and when the parent degrees of these trees are higher. So to summarize, DTTCP handles panel burst, but it's not deadline aware. Another interesting paper from last year's SIGCOMM, Deadline Delivery Protocol, D2, is the first to propose deadline awareness in the data center context. It is proactive and centralized. The nodes request bandwidth based on deadline, and the switches grant the request in a centralized fashion. But because the switches do not have workflow state, D2 grants the request in a first come, first served order. Therefore, during these panel bursts, there are many deadline priority inversions. Further, there are other practical shortcomings of D2. It cannot coexist with TCP, which makes it hard to incrementally deploy, and it requires custom hardware at the silicon level, which makes it expensive. So to summarize D2 is deadline aware, but it does not handle panel bursts well. It suffers from other practical shortcomings too. We now come to D2TCP configuration. D2TCP is deadline aware and handles panel bursts. We propose an elegant gamma correction function for condition avoidance. The idea is flows that have for deadlines back of more and flows through deadlines of closer back of less. So there is a given case of bandwidth between the for deadline flow and the near deadline flow. It is reactive and decentralized, as in contrast D2, which is proactive and centralized, and it takes advantage of space as present at the endpoint. It does not hinder other long-lived non-deadline flows. It can coexist with TCP, making it incrementally deployable. And finally, it does not require any change to switch hardware, which means it's deployable today. And overall, D2TCP achieves 75% and 50%. Fewer miss deadlines than DTTCP and D2 respectively. So here's the outline of my talk. I'm going to talk a little bit about OLDI and then I'll dive into the details of D2TCP. As I mentioned before, OLDIs are deadline bound and handle large data. Therefore, they have a partition aggregate architecture, like a tree. The root node queries the child node, and the child node responds to data. Now, because the OLDIs are a high-level deadline, the deadline budget at the top is split among the nodes on the network. For example, an overall application deadline of 300 milliseconds could mean 70 RPC budget of 50 milliseconds. When a lead node misses its deadline, it sends an incomplete response to the root node, adversely affecting user experience and revenue. So therefore, it is important to minimize the number of missed deadlines. Also, because of the enormity of data, OLDI trees tend to have a high sound degree. Therefore, it is highly likely that many birds from the lead node coincide at the root node, causing packet loss and leading to very high tail latency. These fan and burst are hard to observe in buffers because of two reasons. One, the data center switches use shallow buffers. And two, these buffers are shared with
other legacy flows, including the long-lived TCP flows. Therefore, the packet drops and the fan and burst cause many missed deadlines. The current solutions either over-provision the network today, leading to high cost, or they increase network budget, which means there is less time for compute, which severely affects how sophisticated your algorithms could be. So we all can agree here that the current solutions are far from satisfactory. I'll now talk about D2TCP. To reiterate the design goals are to be deadline aware and as well as to handle fan and bursts. The key idea is to vary the sending rate based on both the deadlines and the extent of congestion. It's built on top of D2TCP. It's distributed and uses per flow state at end hosts. It is reactive, so the senders react to congestion with no knowledge of other flows in the system. I'll now talk about the central idea behind the paper, which is D2TCP's congestion avoidance in combination with deadline awareness. So during congestion, a D2TCP sender varies the sending window based on both the extent of congestion and deadline as per this equation. The current window is assigned to window multiplied by 1 minus P over 2. Here, P is the penalty. A larger P implies a smaller window and therefore a slower sending rate. And a smaller P implies a larger window and a higher sending rate. In this equation, P is our gamma correction function, which we will dissect more. So gamma correction function is a function of both congestion and deadlines, and it is P is equal to alpha raised to D. We adapt the gamma correction function from graphics literature. I will talk more about the parameters alpha and D, but for now, let me just summarize by saying that alpha is nothing but the extent of congestion, and it is same as D2TCP's parameter alpha. It ranges between 0 and 1. 0 means no congestion and 1 means full-on congestion. D is a new metric that we introduced to capture deadline awareness. We call it the deadline imminence factor. It is nothing but the completion window of the flow using the current window divided by the deadline remaining. So naturally, if D is less than 1, it means there is lots of deadline remaining, which means the flow can reduce its window by a lot. And we call those flows as forward deadline flows. Similarly, when D is greater than 1, which means we are short of deadline budget, so you don't want the flow to cut down its window size, and we classify those flows as near deadline flows. Now let's talk about how it works to achieve the effect that we want. So the key idea is you want the near deadline flows with D greater than 1 to back off less, while the forward deadline flows back off more. Here is the plot of the gamma correction function. Along the x-axis, I show alpha ranging from 0 and 1, and along the y-axis, I show the gamma correction function P. I show this graph for like 3 values of D. The green curve is for deadline flows when D is less than 1. The red curve is for near deadline flows when D is greater than 1. And D is equal to 1 refers to the flows which have no deadline. I'll talk about it later. From this equation, as you can see, because alpha is a fraction between 0 and 1, for any value of alpha, a forward deadline flow with D less than 1 leads to a large penalty P, and therefore the window function W as per that equation shrinks more. For the same level of congestion, a near deadline flow gives a small value of penalty P, and the window almost gets retained. Now, D is equal to 1 is interesting because we use that for flows which do not have deadline, so they retain their DC-TCP behavior. In short, the non-deadline flows or the legacy flows maintain their compatibility with DC-TCP. So therefore, gamma connection function here elegantly enables us to capture both the congestion and deadlines. Now let's talk about the parameters really fast. Alpha is calculated by aggregating ECN bits, just like DC-TCP. At the switch side, the switch marks the packet if the queue length is greater than a predefined threshold. The only assumption is that you need ECN marking support at the switches, which is common in today's data centers. At the sender side, sender computes the fraction of such marked packets, averages over time to avoid the spikes, and that directly gives you the alpha. D is our deadline imminence factor, and to recall, it is nothing but the completion time using the current window size divided by the deadline remaining. And to give a small insight on how this arithmetic is done, during the steady state behavior of TCP, the sawtooth leads to the window being constantly varied between W and W over 2. So you can assume that on average the window size is going to be 3/4 of W, and therefore the time remaining will just be the data remaining B over 3/4 of W. This is just to give a small insight. A much more precise analysis is there in the paper. I want to quickly talk about D2TCP's stability and convergence. Any poor estimate of D gets corrected in subsequent RTTs because D2TCP is reactive. Therefore, the control loop is stable to any inaccuracies in the D computation. But it's very interesting to ask the question, what if flows artificially tighten their deadlines? And can they drive the system to a collapse? It's possible, and to avoid it, we cap the value of D at 2 so that the flows are not over-aggressive. Now, this number 2 is not magical. We did a complete sensitivity study and arrived at this number. But in the interest of time, I'm not going to show the sensitivity study results. And at extreme levels of congestion, because of the sheer number of flows in the system, as alpha and P approach 1, D2TCP defaults to TCP-like behavior. So overall, D2TCP avoids congestive collapse. And on the practical side, by maintaining D equals 1 for all the legacy flows, it does not hinder any background or long-lived flows by design. Unlike D-Cube, which requires the new switch hardware, it can easily coexist with TCP, making it incrementally deployable. And because it does not require any hardware changes, except requiring ECN support of the switches, which is commonly available, it's really inexpensive to do. So overall, D2TCP is deadline aware, handles fan and burst, and is deployable today. Let's look at some interesting results. We evaluated D2TCP using a real implementation and a simulation. In the real implementation, we simulate a small network. And in the simulation, we evaluate a data center scale network, and we run production-like workloads. And we use the real implementation to validate our simulation numbers. So we run a small network in both the simulation and real implementation and make sure that our results make sense. And that's the purpose of the real implementation. So talking about real implementation, it consists of like 16 machines connected to a top of rack switch. Each switch has 24 10 Gbps ports and has a 4 MB shared packet buffer. We start with the publicly available DC-TCP code, and we implement D2TCP on top of it, which adds to just 100 additional lines of code. All other parameters in the experiments match those in the DC-TCP and D-Cube paper. And note that because D-Cube requires custom hardware, we could not compare with D-Cube in real implementation. So we compare to them only in simulation. The first thing we want to show is the ability of D2TCP to schedule flows in a deadline-aware fashion. To this end, we do a small controlled experiment in our real implementation. We run 4 flows with varying deadlines, and we capture their bandwidth achieved by each of these 4 flows in our 2 systems, DC-TCP and D2TCP. On the left, I have DC-TCP. Along the x-axis, I show time in milliseconds, and along y-axis, I show the bandwidth achieved by each of these flows in Gbps. And similarly for D2TCP. So from the DC-TCP, you can say starting all the flows get roundabout equal bandwidth, equal share, and then the first flow completes, and then the rest of the bandwidth that got freed up gets equally shared by all other flows. The next flow completes, and so on and so forth. I also show the deadlines, corresponding flow deadlines on the x-axis with the matching colors. So you can see 2 out of 4 flows have missed their deadline. Whereas in D2TCP, the flow with the nearest deadline gets the largest share, while all other flows get a small share. And once that flow completes, the next flow grabs the high share, while the rest of the flows share a much smaller share, and so on and so forth. So, and finally, all the 4 flows meet their deadline. So this is a very controlled experiment. It's not supposed to model real workloads. This is just to show the proof of concept. Our at-scale simulation, we simulate a 1,000-node cluster with 25 racks and 40 machines per rack. And all the 25 racks are connected to a non-blocking fabric switch to simulate a factory topology, which is common in today's data centers. We evaluate, we do all our simulations using NS3, and we calibrate the unloaded round-trip time of our network to 200 microseconds, which matches today's data centers. And all our DC-TCP and D-Cube implementations match the specs that is there in their paper. As far as workloads, we evaluate 5 synthetic OLDI applications, which model applications like search. We take the message size distribution that is available from DC-TCP and D-Cube paper, and we distribute the message sizes around the mean values of 2 to 18 KB. We calibrate the deadlines very carefully to match the absolute results from DC-TCP and D-Cube. And we use random assignment of threads to nodes to abstract away the artifacts that arise due to mapping. And we have some long-lived flows that constantly send data to the root, again, to simulate what will happen in a real data center. And finally, we maintain a network utilization of 10 to 20%, which is typical of today's data centers. The first graph we want to see is the bottom line missed deadline comparison across all the schemes. Along the x-axis, I vary the fan-in degree of the OLDI applications, which affect the fan-in bursts or the size of the fan-in bursts. And along the y-axis, I show the % missed deadlines. We compare 4 systems, TCP, DC-TCP, D-Cube, and D2TCP. Note that because the y-axis shows the % missed deadline, lower is better. So from this graph, as you can see, as fan-in degrees increase, all the systems experience more and more missed deadlines due to fan-in congestion. It's interesting to note that TCP, the missed deadline from the TCP increases greatly as compared to other systems. But it's much more interesting to note that around the fan-in of 40, both DC-TCP and D-Cube still miss 25% of their deadlines. At the same fan-in of 40, D2TCP just misses around 7% of its deadline. The next thing we want to verify is that D2TCP does not hinder the legacy long-lived flows bandwidth. And to that end, we compare the bandwidth achieved by long-lived flows under all the 3 schemes, all the schemes. So similar to the last graph, I show the fan-in degrees of the OLDI application along the x-axis increasing, and along the y-axis I show the long flow bandwidth normalized to TCP achieved under DC-TCP, D-cube, and D2TCP. So as you can say, overall all the schemes achieve round about the same long flow bandwidth. But it's important to note that D2TCP comes within 5% of TCP's bandwidth across a wide range of spanning degrees. So I'm slowly inching towards the end of my talk. The next two talks are very related. They address the issues of tail latency and deadline awareness. But I'm not going to steal their thunder, so I'm going to let them present their talk. But I'm more than happy to take any comparison questions later. And finally, to conclude, D2TCP is deadline aware and handles fan bursts. It requires 50% fewer missed deadlines than D-cube. It does not hinder background long-lived flows. It coexists with TCP, making it incrementally deployable. And finally, it requires no hardware changes, which means it's deployable today. And so we believe that D2TCP is an elegant and practical solution to the challenges posed by old DIs. Thank you.
Do you have time for questions, Phil?
Hey, Phil Willis, Stanford University. So why gamma? So in graphics, gamma is because our eye responds non-linearly to luminosity. So are there other functions that you try, or just that this one worked pretty well and it's nice and it's smooth, or why gamma correction of all functions?
Oh, the question is whether you have tried any other functions other than gamma functions, and what?
Yeah, I mean, it's not like we have sort of a similar response to latency or something like that. So is it just it happened to be that it worked well, or did you try other things? You know, what didn't work?
Actually, an honest answer is it happened to work well, and it showed good performance. And we have not really done a functional move with other functions. So, yeah, the honest answer is it worked well, and so we stick to it.
Congratulations on picking right the first time.
Rick McGeer from HP. I'm curious about the response. The way you correct for congestion is by raising alpha, right? Is that alpha gets constantly recalculated in response to ECN notifications?
That is correct.
Okay, so now let's consider the case where you have a whole bunch of flows with tight deadlines. So D is 2 are very close, and alpha originally starts out very small. Right. The real question is how rapidly does alpha then converge to 1? Because you'll want alpha to move up to 1, or else you'll have congestion problems, I would think, right?
Okay. First up, alpha is not instantaneous. So the condition feedback gets averaged over time to avoid spikes. So alpha itself is exponentially averaged. So alpha is the fraction of marked packets exponentially averaged over time to filter out the spikes. So, and alpha remains the same as it is in DC-TCP, or how it was defined earlier. So, if I get your question right, D2TCP does not affect or in any way how fast the alpha will vary or converge to 1.
Okay, so then I have the following question, with that being the case. Suppose let's consider that scenario. Did you run an experiment where you had a large number of tight fan-in jobs, and with alpha set very low, so basically everything was backing off at 1 minus a very small number.
Oh,
right. So basically very slow back off to start with, and just what happened.
Okay. I want to show a couple of slides. Basically, you're asking that you do not want to restrict the cap on D. Is that your question?
No, I mean, so suppose take cap on D that you've got, D equal 2.
Okay.
Right? So now you've got 1 minus alpha squared over 2, but alpha is a very small number, right? So, so the question is, what happens, right, when you have a whole bunch of flows that are backing off very slowly?
Well, I think that will lead to the condition of the number of marked packets will increase, and therefore, let me correct my earlier statement, alpha will increase faster than DC-TCP in this case. That's right.
All right, thank you.
Yes.
It is Prani, MSR, Cambridge. I enjoyed the talk. So in one of the slides, you made this claim that D2TCP does not lead to congestive collapse. And I'm just trying to understand that a little bit better. So even with this trick of your capping D, you can easily get into scenarios where, because effectively what you're trying to do is simulate EDF, earliest deadline first, with an endospaced approach. And it's pretty cool that you're able to do that. And EDF is optimal when all deadlines can be met. But in scenarios where all deadlines cannot be met, you can easily go into situations where you prioritize flows that have tighter deadlines. Even with this cap of D is equal to 2, you miss those deadlines. Because you've given resources to flows with tight deadlines, you have this cascading effect that subsequent deadlines are missed. And there are ways to avoid that. I just didn't see anything that in this solution that lets you avoid that problem.
Yeah, I think this slide is a little soft in the sense that at extreme cases, definitely you are protected on either side by DC-TCP and TCP bounds, of course, mathematically. As alpha and P approach 1, you're protected. And that's all this slide says. But coming back to your original question, that's right. So when a lot of flows miss their deadline, because we do not do anything like flow quenching or adjust, and because they have tried meeting their deadline and therefore they have increased their sending rate, they have increased queuing. And therefore it will lead to a few more flows missing the deadlines. And I do not have a way to avoid that. Yeah, I mean, your observation is right.
Thank you.
One last question, KK, as Chira sets up.
Hi, KK from Stanford. So the thing that appears to me when you were comparing DC-TCP was that you seem to have sacrificed fairness to a very large extent, at least on the graph. So can you tell me a bit more about what fairness property does the D2TCP would have, for example, for flows that have the same deadline or something of that sort?
I'm sorry, I kept on.
Is there any analysis on the fairness of D2TCP?
Sorry, I'm still not getting it. Can you pardon, can you say it again?
Why don't we take this offline? We're running out of time.
I'm sorry.
Let's thank the speaker again.